Hello everybody, we have already seen skip lists, their structure and how the dictionary operations are performed in skip lists. In this current segment, we are going to analyze a skip list. We are going to look at the number of levels, the space complexity and the search times. Let us now focus on the number of levels. We already have an intuition for the number of levels. The number of items in each level is roughly half the number of items that was in the lower level, and therefore, we expect intuitively to see about order of log n levels on expectation, and this intuition is in fact correct, and we now would like to formally prove this. So, how do we do this? Let us first begin with an item x okay, and ask ourselves what is the probability that x is raised to some level I or more, and this probability turns out to be 1 over 2 raised to the I, which is essentially the probability that a fair coin coming up heads I times before the first tail. And this fits very naturally with the way in which we perform insertion within a linked list. Now, we ask ourselves, okay, if one item has that behaves in that manner, what is the probability Pi of at least one item reaching level I or more? Okay. And what is this Pi? Well, we use a very simple technique for this, the union bound. This Pi is at most n times the probability that one of the items will reach level I or more, and simple application of the union bound. And when we look at this and we let us say we set I to be 3 log n, now Pi is at most n over 2 raised to the 3 log n, and here log is to the base 2. So, the denominator becomes n cubed, which implies that the probability Pi is upper bounded by 1 over n squared. And if the constant was a little bit different, then for example, if the constant was a higher number, say 5, then we would in fact get 1 over n to the 4. So, in other words, we notice that for as I goes to say some c times log n, the with probability c minus 1, 1 over n to the c minus 1, the number of linked list levels will stop at some level less than c log n. So, this to state it more succinctly, the number of levels is less than in particular 3 log n with high probability. So, this is exactly what we need. Now, let us look at space complexity. This is the amount of space we need to store the data structure, and notice that each item in the skip list has a constant number of pointers. So, there is one pointer pointing to a level up and another pointer pointing to an item, the replica of the item in one level down, one to the left and one to the right. So, there is 4 pointers per item in the skip list. So, it really does not matter, we do not need to count the number of pointers, but we just need to count the number of items, and that will give us a handle on the space complexity of skip list. And so, let us focus on that. So, let us look at the number of items, expected number of items at level I. We already saw that each item gets promoted to level I with probability 1 over 2 raised to the I, and there are a total of n items. So, that expected number is n over 2 raised to the I. And so, let us now do a summation over all possible levels, and that is simply going to be summation I equals 0 to infinity n over 2 raised to the I, and we can bring n outside, and within the summation we have 1 plus 1/2 plus 1/4 plus and so on, which is at most 2, and therefore, we get our bound of O of n on expectation. Now, let us look at searching within a skip list, and let us just quickly recall how searching works. If you are searching for 68, you may have to move forward, overshoot, come back and go one level down. Again, move forward, come back, one level down, move forward, overshoot, come down and so on until we find the element. So, in other words, to search for an item, we alternate between making forward moves until we overshoot the searched item, and then we step down one level. And so, since there are order of log n levels, we have seen that to be true with high probability. We do not need to worry so much about the second step. We can tack on an order log n additive factor to our search time to account for that. So, we only have to worry about the horizontal, the forward moves within a level. Notice that if when you are making forward moves within a level, except for the so let us look at the forward moves that happen. So, except for the two ends, say the 34 and the 17, this when we are considering this level 1, except for those two, the rest of them are items that do not occur in the level above. Okay. So, that is crucial, because now let us look at the number of such items we will encounter in each level. So, now let us focus on one level, and let us look at each item in that level. The probability that an item is not raised to the subsequent higher level is exactly a half. So, when we step down into a level, that particular item is is represented in the next level, and if we overshoot, then we may encounter an item that could potentially be present in the level above, but all the other items they were not raised beyond that particular level. And so, in other words, each one of those items, when the particular coin was tossed, it showed up tails, and so they were no longer raised. And what is the probability with which that tails occurred? That was it's a half. So, now let us count the expected number of items that our search procedure will encounter at each level. There will of course be the two items that we will encounter that are promoted, and then because it is a geometric progression within a level to get to an item that actually produced a heads and therefore was promoted, the number of such items can be at most 2 on expectation. So, on expectation we will see at most 4 items per level, and recollecting that there are a total of O of log n levels with high probability, the expected search time is O of log n. And once we understand how search works, it is not very difficult to understand how insertions and deletions work, and what their and to also show that their running times are also bounded on expectation by O of log n. So, this brings us to the end of this segment on analyzing skip lists. And as you can see, the skip list is a very elegant data structure, and simple analysis shows us that it works quite well. And in fact, it also works quite well in practice, except for the one drawback that each item requires 4 pointers, which is perhaps the only drawback that at least I can think of. So, in the next segment, we will move on from data structures into an algorithm. We will see an algorithm for a particular problem, the min-cut problem. Thank you.